Okay, so I brought up this slide from 2 lectures ago when we discussed with you examples of linear maps. Excuse me, is that your response to being tired? Never mind. I brought this slide from 2 lectures ago when we discussed with you examples of linear maps. It's not a complete slide, that what we had before that, something which I called matrix type linear maps. These are the linear maps which exist specifically between these two types of vector spaces, between n and m tuples, and which are implemented via matrix multiplication. This is something we discovered with you 2 lectures ago. Back then, and then after that a few times, I told you that 99% of the linear maps in the yellow book are linear maps of this type, of the matrix type. And the first thing I'm going to discuss with you today, I'm going to present some support for this claim. I'm going to show you that actually every linear map between n tuples and m tuples is always implemented by a matrix. So in fact, this lemma, which we discussed with you 2 lectures ago, it becomes of great importance because every linear map is in fact every linear map in this setting, between n tuples and m tuples, it is a map which is given by matrix multiplication. Let's just look into that. The proof of this result, the proof of this result, not only it proves the result, it gives you the mechanism, the recipe how to recover the matrix underlying the map. In fact, this mechanism, you're going to use it a few times in the yellow book. A few questions in the yellow book relies exactly on this mechanism. So this is something which I called on my slides, I called matrix representation theorem. And that reflects the fact that the purpose of this slide is to show you that every linear map, so I'm going to call it a theorem, matrix representation theorem, every linear map between n tuples and m tuples, if T from Fm to F, from Fn to Fm is a linear map, then there is a matrix of suitable size, m rows and n columns, such that this matrix implements my map via matrix multiplication. F, symbol F, it's a thing which we use all the time. It's a symbol which represents either rationals, reals, or complex numbers. So here's the proof. Like I said, the proof not only is interesting in its own right, it gives you this recipe which will be helpful in many questions in the yellow book, because in many questions in the yellow book, the question will go like this. Here's a linear map. Please recover the matrix which implements that linear map. And the proof actually does exactly that. It tells you this mechanism, how to recover that matrix. So what you do is this. First you fix a basis, and this boldface E, that's the symbols we use to denote the standard basis in its n elements. It's here in the domain of my linear map in Fn. So this is a standard basis in Fn. Then proof goes like this. It says, okay, so let's just start off with the element in Fn. I call this element x. Components of that element, x1, x2, and xn. It's a regular convention which we use. If we use the letter x for the vector, for the n tuple, then the same letter x is used for the components of that n tuple. So given that this is a basis, and in fact given that this is a standard basis, we certainly know that this element will accept the following representation for this standard basis. This claim, it borders on the level, borders on the line of triviality. So what I will do now, I just say this: if I now compute T of x, given that T is linear map, it is linear map. That's the assumption. That's the place where we use this assumption that the T is a linear map. It's not going to work for any other maps. That's the linearity. We can apply T individually to every element of my basis and then combine them with the same coefficients, x1, x2, xn. This is just linearity. Now the next step will be this one. Listen to this. T of E, all of these vectors, T of E1, T of E2, T of Ens, given that my T takes n tuples into m tuples, each of these vectors, T of E1, T of E2, T of En, they are by themselves, they are m tuples. M for Mary. I'm going to introduce notations for the components of those n tuples. I will need them, okay? So the strategy for indexing these components will be like this. Look at this. T of E1, it must be m tuple. I'm going to introduce the names for the components. Here's the names which I choose. Look at this. A11, A12, AM1. So my convention is this. The first index of my little a is the one which indexes the index the components. I'm sorry. And the second index, it's the one which is basically the index of my E vector. You see, that's the convention which I use. I am in a position to introduce this notation because at the beginning we know that T takes n tuples into m tuples. Now if I move on with the same convention, T of E2, I just follow the same convention. The first index is the one which is changing across my m tuple, and the second one is the index of my E vector. That's the notation for the second m tuple, and I'll have altogether I'll have n such m tuples. The last one, according to my notations, according to my strategy, will be like this. The second index here is n for Nicholas, is the same as E, and the first index is again represents the changing index within the m tuple, m for Mary. These are just the notations. We have the right to do this because we know that the T is the one which ends up in Fm. Yeah, that's what I said here actually. All of these T vectors, they are from Fm, so I can introduce the notations like this. Now, what I'm going to do is this. I'm going to take all of these m tuples. That's quite a huge, that's quite a lot of writing, in fact, but I hope we can survive that, and we'll do it in a smart, structural way. I'm going to take all of these m tuples I just introduced for my T vector, and I'm going to plug them in here in my expression for T of x on the right-hand side. If I do that, and if after that I combine all of my n tuple, all of my m tuples, I will end up with the one single m tuple, and I'm going to write the components of that m tuple. Here's the writing. Look at this. So my T of x on the left-hand side, and now I'm writing the components of one single m tuple, which appears if you just sub in all of these notations we're introducing, combine them together. The first component will be x1 times the first component here, then x2 times the first component here, all of the same strategy, the xn times the first component here. That's the first one, you see. The second component of this huge m tuple will be x1, or this x1, sorry, times the second component in this m tuple, then x2 times the second component in this m tuple, x3, x4, and all of this, and the last one will be xn, and the second component in this m tuple. Here it is. These two already, I hope, deliver the whole idea what's going to happen next. Now I can open the whole thing. Yes. Well, yes. So that's my m tuple, and the last observation which I need to make is this. Actually, that this m tuple we just wrote up here. You can alternatively look at the same m tuple as a matrix multiplication of your x vector and the matrix like this. You see, in this matrix, every column of this matrix. Every column of this matrix is exactly the T of E1, T of E2, T of En. And that's basically the end of the proof. If I just give a name to this matrix, so if I call it A, that will be the matrix with m rows and n columns, and my T map is implemented by this matrix. it's one of the very good proofs because it gives you the structure of the whole idea behind this claim, and it gives you the recipe how to do this in every particular instance. All you need to do to recover a matrix of a linear map, to recover the matrix of a linear map, you need to apply your linear map to the elements of the standard basis, like I did here in the abstract setting. You will be doing it in the particular numerical settings most of the time. You need to apply this T to each element of the standard basis and then collect the results as columns. That's all there is to it on a algorithmic side. And the reason why this works, it is exactly right here on the screen, why this works. Any questions? So now we know that any map between n tuples and m tuples, or the other way around, between the m tuples and n tuples, it is always something which is implemented by a matrix. And now you know how to recover that matrix. Our next objective is to see something similar when you look at a linear map between abstract vector spaces. No longer the vector spaces which are m tuples or n tuples like here, but anything else, as a matter of fact. Something similar still holds. It's something I'm going to call the matrix type maps of second type, or second type matrix type maps. Or I'll think of a terminology. And that's actually a very interesting fact about linear maps. Okay. So once again, now we know that in a setting of n tuples, linear maps are simply structured. It's basically just multiplications by matrices. That's all there is to it. It turns out that in a setting of any other vector space, something similar still holds. With some adjustments, you can see matrix multiplication even if you are in a setting of a vector space which has nothing to do with n tuples or m, like functions, for instance, or polynomials. And that's something we're going to discuss for the rest of today's lecture. I will need to do some preparations before we can actually see the actual result. We can actually see how the structure, metric structure, appears even if you don't deal with the n tuples and m tuples. So I'll start with a bit from a distance, from some results which you may think at the beginning they have no relevance to matrix type structure, but eventually you'll see the relevance, I hope. Let's just do this. So the first thing I'd like to discuss with you before we reach this result is what I call the operations on linear maps. Yeah. Just happened. Yeah, that's right. So it's a slide which I call operations on linear maps. It's the mechanism how to build new linear maps having existing linear maps. Okay? And that's something which you can think of in any setting, in the setting of any vector spaces. So I'll start off with the three different vector spaces. I'm going to call them V, W, and Z. 3 different vector spaces, abstractly chosen, no connection with the n tuples or m tuples. I'll assume that I have 3 maps. I'm going to call them T, S, and R, like this. So these are vector spaces. These are maps. There are 3 operations which appear very often, which you apply very often to maps or linear maps, to any maps, not necessarily linear maps. That's why I didn't say that T, S, and R are linear. In fact, these operations, you can build them on any maps. Sum of linear maps, and that's how you write this, T plus S. That's the map which will take V into W, because T takes V to, and that's how you define it. Sum of T and S on a vector, by definition, that's my symbol, colon next to equal sign. It's just the sum of the T on X and S on X. Scaling of a linear map, that's how you define scaling. And the third operation, which will appear often, it's a composition, that's how you write it, R circle T. And look, it's a one which is a little bit more involved than just sum and scaling. That's how you define it. And these are the operations which I will need in my discussion of linear maps in a general setting. So Yeah, that's right. So look at the domains and the codomains. For the sum and scaling, domain of the new map and the codomain of the new map, they are the same as the domain and codomain of components, T and S, individually. For the composition, it's a little bit trickier. Look at this. The composition is the one which works like this. You take for the domain of a composition. This is a composition map, so this is a For the composition, the domain is the same as the domain of T, the element which is on the right-hand side of your circle, and the image or codomain is the codomain of R, the one which is on the left-hand side of your circle. In fact, that is clear from this formula as well, because you apply your T to the X, so X is the element of V. X is an element of V. First you apply your T to X, and T takes this X into an element of W, and then you apply R to this new element in W, and this R takes this element to Z. So this T element, T of X element, that's the element of W. Like this. Okay. You also may think of a composition as a double stage linear map. So first you just take your V into W by means of T map, and then you take W into Z by means of R map. That's another way of thinking of a composition. That's another way of thinking of composition of two linear maps. Another interesting thing is when you write composition, the order in which you write symbols is important. I mean, in the current setting, R circle T makes perfect sense, but if you try to make sense out of the writing T circle R, this is no longer make any sense, because R goes into Z and your T has no action on Z. T acts on V. So in a composition, it's one of the first examples of, well, actually not the first one, of course. It's one of those examples of operations on objects which is not commutative, the one where you're not allowed to swap the terms around freely. The other example of such operation, of course, matrix multiplication. It's another example of an operation which doesn't allow you free swapping of elements around. Okay, so the main thing which you need to know about this free operations, and this is the main thing which I collected into a lemma. It says this: if these original T, R, and S are linear maps, once again, the construction of these operations, it has nothing to do with linearity. You can construct similar operations on maps which are not necessarily linear. However, we deal only with linear maps, so that's why I have this lemma. If the original maps are linear, these three new maps we just built, sum, scaling, and composition, are also linear maps. That's the main thing which we need to know about this free operation. So these free operations, they give us a way of building new linear maps on having some existing linear maps at our hands. It's done. I have a proof on the slide of this lemma, and if you want to see the proof in full, or if you want to produce a proof in full, you need to check those two little a and little b requirements on a linear map. You need to check these requirements for each of these linear maps: for the sum, T plus S, for the scaling, lambda T, and for the composition, R circle T. As far as I remember, yes, this slide has everything. Writing-wise, it's a long proof. I'm not going to open everything. I'll just show you argument for the composition. For the rest of it, I encourage you to try to recover the proof on your own. If you struggle, you can open the slide and see the details. So I'll check these two requirements, little a and little b requirements, which you need to check if you claim that something is a linear map. I'll check it only for this operation, for composition. So here it is. I need to lift it up a little bit. So I'll check requirement. So it's a proof. I'll check requirement A, and I'll check it only for the map R circle T. So requirement A says that if you apply your proposed linear map to a sum of vectors, the result must be sum of the individual applications of this map. So if I apply R circle T to x plus y, first I'm going to use what it means. I'm going to interpret R circle T. That's the interpretation for R circle T. I first apply T to the sum, and then I apply R to the result. That's the first step. That's the step here. That's the one which is based on this identity. Now I'm going to use the fact that T is in fact linear map. It's the assumption here. T is a linear map, so I can break this T of x plus y into T of x plus T of y. Next, I'm using the fact that R is a linear map, so I can split this R of sum of T of x and T of y into individual R applications, R of T of x and R of T of y, and then I can use this in reverse. I can use this in reverse and just say each of the terms here, it's R circle T of x and R circle T of y. That's all there is to it. So basically, it's a very simple proof, which goes like from beginning to the end, step after step. At each step, you just make a proper reference to the something either in the assumptions, like T or R linear maps, or something in the definitions, and that's the end of it. Very similar and very simple proof again works for the second part of linear map definition, for the scaling one. Here it is. If you apply R circle T to a scaled vector, and I use letter mu for the scalar, then first I use the interpretation of R circle T. This is the interpretation. Then I use the fact that T is a linear map, so mu can be taken out. And then I use the fact that R is a linear map, so mu can be taken out of R as well. And then interpretation of R circle T. And that's the second requirement of a linear map is verified. Any questions? Okay. Any questions? All right, the next step towards my objective, and remember my objective is to see to see some analogs of this matrix representation in a general setting, in a setting of an abstract vector space. The next slide in this direction will be something actually we discussed already with you to some extent on Thursday last week. And that's something which I call vector coordinates as linear maps, or as linear map. It's something we actually discussed with you already. When we discussed with you image of a linear map on Thursday. Look at this. Here's my setting. Again, I have a vector space V. I'll fix a basis in this vector space B. On Thursday, we discussed with you a very interesting example of a linear map. That's the map we discussed with you on Thursday. Look at this. It's a map which takes m tuples into elements of this V vector space. Back on Thursday, I used letter T, just generic letter T to denote that map. This time, I introduced a special symbol which will be fixed to this type of maps from now on. J sub B. This sub B reflects the fact that the map actually depends on the choice of a basis. Okay, and the map itself, the formula we have is like this. If you take an m tuple from here, the action of your J on this M tuple will be just a linear combination of the elements of the basis with the coefficients from the M tuple. On Thursday, we proved with you that this is a linear map. We made an effort and we did this. So that's what's here. It's a linear map. It's a linear map. We proved this earlier. In fact, we proved this on Thursday. We proved this in relation to a different subject. We discussed something else. We discussed images with you back on Thursday. And this is a linear map actually which covers the second category of subspaces if you take the image of this linear map. Now we're going to use this. You will see that this map actually useful for the other purpose as well. We're going to use it in relation to our new objective, matrix representations of linear maps. So, give me a second, please. Okay, right. In conjunction with this map, I'm going to introduce a new map, which I'm going to call, that's it. I'm going to call I sub b. They come in pair. I mean, in fact, it will be the inverse for my j. Look what it's going to do. For any vector x in your vector space, given that this is a basis, we know that my vector admits a representation like this as a linear combination of elements of my basis. Okay? My map I sub b, what it will do, look at this. It will do this. For this vector x, it will assign the coefficients which appear in this representation. Remember this symbol? It's something which we call the coordinate vector of x with respect to the basis b. This is exactly the M tuple. Here it is. It's exactly this M tuple, which consists of the coefficients from here. And this map, which takes the vector x into this M tuple, that's a map, isn't it? It's just we took a vector from V and we constructed an M tuple in some way. This is map, in fact. In fact, it's not just a map. It's a map which acts in reverse to this J map. If you take an M tuple, if you build this linear combination and then you apply I map, it will do the reverse action. So that is exactly what you said here. The IB is the inverse map for the JB, and the other way around. JB is the inverse map for the IB. Okay? In fact, you know this map very well. I mean, you've done it a few times already. You by having a vector, you reproduce the coefficients which make this vector as a linear combination of a fixed basis. So on the computational side, you computed this map quite a few times. We're just giving this procedure you used to do so often. We now give this procedure and this new name. It's going to be a map. And in fact, the lemma on this slide says it's not just a map, it's a linear map. So it's a map which is subject to the condition A and the condition B. Okay? It's one of the fundamental maps which you need to remember. This is one of the examples of the maps. This is another example of the fundamental maps which you need to remember all the time. The third example was on Thursday. We discussed it on Thursday in relation to the null spaces, in fact. Right. Some of you who will continue learning mathematics to the higher level, you will learn one day that if you have a linear map and if you compute the inverse to a linear map, the inverse will always be linear, no exceptions. However, in the current circumstances, because we're not studying mathematics at that high level, I think the direct proof will be a better exercise for us. Given that you need to do it, given that in the yellow book, there are so many questions where you need to show your skill of verifying that something is a linear map. This slide gives us an opportunity to do this verification once again and to practice it once again. So let's just try to prove it directly why this new map, IB, is linear. Proof. It's the time, 35 minutes. So I'll start off with two vectors. X and Y, in my vector space V. For each of these vectors, I can, in principle, find the representation of these two vectors with respect to my basis. And here's the representation. So for these two vectors, I can find this coordinate vectors with respect to the basis B. And what I mean by that is that my vectors admit the following representation. X has a representation like that, and Y has a representation like that. You may notice sometimes when I do this dot type of writing, when I have like n elements and or I plus them or I put them in columns, so when I use dots to hide some elements, sometimes I use I write the first two and then the last one after the dot, or sometimes I write one and then the last one after the dot. Sometimes I choose one way of writing, sometimes I choose the other way of writing. Well, if you ask me why, I do it when I choose only one. When I choose to write only one element, it's just of course like for the purposes of saving time. When I absolutely sure that it's not going to cause any confusion. That's why I do this. So because we write so many n tuples and sums, that's why I start dropping the second one. You see, I just did a few times with 2 first, and then I dropped it only for the reason because I want to save some time, and I'm sure that doesn't cause any confusion. Anyway, so I fixed 2 elements. For these 2 elements, I can find the representations. Here it is. So now I can argue part A of being a linear map. I apply my, well, that's how I argue actually. If I add up these 2 vectors, x and y, if I add the right-hand sides here through simple manipulations, which I hide by these dots, the representation for the sum will be like so. Hence, if I go for the IB of x plus y, that's what the IB is of a vector. All I need to do, I need to collect these coefficients as an n tuple, m tuple in fact. Next, because of the way we add m tuples, I can split this into some of these 2 individual m tuples, and each of them individually, it's the IB of x and IB of y. This is the end of the verification for part A. I used to say it many times, when you prove something, you always borrow things from the past, from your baggage of knowledge. And on this occasion, the borrowing happens here, at this particular place, not other places. All other places, just a reference to the definition of what IB is. The borrowing happens here, where we just say that if you sum m tuples, you sum m tuples in a per component way. That's the place where the borrowing from the past happens. Okay, well, similar argument works for the B part. If I argue B part of linear map, first I make the observation that if I scale a vector, from here, through simple manipulation, this is as good as this. Through simple manipulation, this is as good as this. And hence, when I apply IB to lambda x, by definition of IB, it is here. That's the definition of IB. I can't move the slide right now. I'll move it in a few moments. This is this m tuple. Now I borrow things from the past. I know when I scale an m tuple, this is as good as scaling every individual entry. This is a place where the borrowing from the baggage of knowledge comes in. And then I use the definition of IB. And that's the end of the formal proof why this map IB is linear. Okay, any questions? It's a technical lecture. I told you from the beginning. Today will be a relatively technical lecture, but trust me, in a few examples, when you try a few examples, and we're almost there, we almost reach my objective. I'm almost there to show you what I mean by the matrix type map between abstract vector spaces, not specifically m tuples. We're almost there, and we have time to see that. When you just try a few examples, all of this will come together in a nice, beautiful picture, trust me. And you say, oh, wow, now I see. Trust me, there will be a wow moment in your understanding. It's not an easy lecture, so if you're just struggling to understand everything I say, right now it's not a bit, don't get upset. You will have a video recording, you'll have the lecture notes, you will revisit this, you will do a few examples, and you will have your wow moment. Okay, so the last slide, which is like a brings everything together. I'm sorry. Yeah, the last slide which brings everything together. Yeah, that's the one which I call matrix type linear maps number 2, because that is about the matrix type linear maps, but this is a new type of matrix type maps. Look at this. So original type 1, that's the one which I showed you today at the beginning of the lecture. That was the type which was acting between two m-tuple spaces, and that was defined via a matrix, like this, via matrix multiplication. X was an element in Fn. Okay, so A was a matrix of the appropriate size. F was one of the number fields, Q, R, C. That's a type I just recalled for you at the beginning of today's meeting. Okay? Now look what's going to happen with the type 2 maps. For the type 2 maps, now I'm going to just give you the general setting. 2 vector spaces, no longer a particular type of vector, any vector spaces, V and W. Function spaces, polynomials, matrices as vector spaces, any vector spaces. So, in order to introduce the second type of maps, and by the way, you see I reflected the dependence of this map on the matrix A by using this subindex A. It's a normal practice. So I'm going to introduce 2 bases. One of them is going to be B with elements V1, V2, Vn. It's a basis in V vector space, and C will be a basis in W vector space. Okay, that's another 2 elements which I need to build the construction. It's not easy. It's not an easy construction at first sight, but there's a huge. There's a very strict logic and structure behind it. And when you understand that structure, that will be your wow moment. So that's I think that's all I need to do to introduce my map. 2 vector spaces and 2 sets of bases in each of these vector spaces. One of them will be B, the other one is C. So my map, it will act between V and W, between this V and this W. Domain is V, our codomain is W. It will depend on each of the elements I introduce. It will depend on the choice of these bases. It will depend on the choice of these bases, and in fact, it also will depend on the choice of the matrix up here. That's why I reflect this dependence as subindices here. And look how this map is going to act. In short, in the yellow book, when you get the grasp of it, you will see that in short, people normally write something like this. So let me just, because it's a long symbol to write, T sub ABC in capitals. It's a long symbol to write, so for the rest of the slide, I'll just use the letter T just by itself as an abbreviation to this. But every time I write T, I mean this T, which depends on A, B, and C. So in yellow book, you will often see something like this. That's how we define this map. It's a very short way to write this, and I'll give you now the explanations what exactly this one little line contains. Look what this line contains. I'll take you through this line a bit. I'll take you through this line. You start off with the element in V here. You need to produce an element in W. That's how your map acts. And that's how you produce, it's a free-stage construction of this result, T of X. Look what you do. First, at first stage, you split your vector into representation in terms of the basis B. You can always do that. It's a first stage. That's a stage which is done by the, it's a first stage, I'm sorry. Then, Then you collect all of these coefficients into n tuple. You collect all of these coefficients into n tuple, and then you build new sets of coefficients, m tuple. I call this mu1, mu2, and mu sub m. How do you do that? That's how you do it. You take these sets of coefficients, and you multiply by this matrix A. That's the second stage of the construction. We're not here yet. And now at the third stage of your construction, you take these new sets of coefficients, and you take a linear combination of these elements in a C basis. And that's how you finally arrive into W. Three-stage construction. You start off with the element in V, right here. You split it into the representation. You end up with the n tuple. You multiply it by a matrix. You result with m tuple. And then you use these coefficients as in a linear combination with W vectors, with the basis in C. The result is something in W. Is the end of your construction. This three-stage construction, it is normally encoded like this. You see, you take a vector, x. For this vector, you find the coordinate vector with respect to b. This is the lambda n tuple. Then you multiply this by the matrix A right here. And the result must be the same as representation of the tx with respect to C basis. Here. This one little line, it just contains all of these three stages. Given such a complexity, the question arises, why this is a linear map? The answer to this is immediate, given how much preparation we have done so far. Look at the answer. All of these stages I just presented, I can now wrap them into this IB and JB maps we just discussed with you before. Look at this, what happens? That's how it works. My x vector at the first stage here is taken to the coordinate vector of this x with respect to the b basis. This is a map which we called IB in the slide before. Then this result is taken to the matrix product. This is a map which is TA map, this map. It's a first type matrix map. And then the result is taken into linear. This is the map J sub C from the slide before. So in fact, these three stages, it's a combination of the IB map, TA map, or JC map. Or if I use the language of operations on linear maps, I can now say that the T sub A sub B sub C, and that's a typo, it's a composition of the maps. JC is supposed to be here, and IB is supposed to be here. First you apply IB, then you apply TA, and then you apply JC. V is taken to Fn by IB, then taken to Fm by TA, and then taken to W by JC. This is two compositions in a row. And because of the lemma we discussed today, because we know now if you compose linear maps, the result will be linear map, we can now easily and safely claim that this is a linear map as a composition of individual linear maps. As a composition of individual linear maps. Today is Tuesday, right? On Thursday, we will see that any map, absolutely any map between absolutely any vector spaces can be given such a structure. Remember the result we started off today? I told you that any map between Fn and Fm always has metric structure. With this extended interpretation of the metric structure, with this three-layer or three-stage metric structure, any map between any two vector spaces will be a map will be a matrix type map. That's something we will see on Thursday. Any questions? Well, we have 4 minutes left. I'll show you one example of this construction. It's a simple example. You'll see more involved examples in the yellow book. After a few examples, you will have your wow moment. You will see all of these structures in one single piece. But I'll show you one example today, and then we will be done. Unless, of course, you have any questions. Any questions? No? It's a question 62 from the yellow book. The question discusses the map G between two vector spaces, polynomials of degree 2 or less into polynomials of degree 2 or less. So G is a map T sub A sub B sub C. That's the notation from my slide before. Given that you have V and W here identical to each other, the question suggests to choose these two bases, E0, E1, E2, E0, E1, E2, identical bases for B and for C. E0 is a polynomial 1, E1 is a polynomial x, E2 is a polynomial x squared. By now, I hope you know that this set of polynomials is a basis in this vector space, polynomials of degree 2 or less. In fact, this is something we call the standard basis in this vector space. Is a matrix in that question. I think all question expects from us is to find the direct formula for the map T sub A sub B sub C. This three-stage map from the slide before. Just one single direct formula for these three stages. For these three stages. Yes. It's a simple question. All we need to do, we need to carefully combine these three stages into one single formula. And that's the combination. Look at this. I start off with the random element in my domain, V. It's a random element with randomly chosen coefficients, A0, A1, A2. This is a representation of this element in terms of the basis, B. So, if you ask me what's the coordinates of my vector P with respect to the basis B, that's the triple of numbers, which is exactly the coordinates. And that's the result of IB map. IB map applied to this P polynomial. So that's the formula. This is one single condensed formula which hides these three stages from the slide before. So my representation of G of P with respect to the C basis must be a matrix product of this vector and A. It must be this. When I compute this product, if I just compute this product, this is a computation. This is simple matrix multiplication with the column vector A0, A1, A2. And this is this element. This is this element. If I need to recover the G of P itself, and G of P must be the element in the codomain, which is a polynomials vector space, this is a recovery of GP. What I do, I take these numbers in my triple, and I put them next to the basis in the codomain, E0, E1, and E2. This is the first entry in this triple, next to the corresponding basis element. This is the second entry in this triple next to E1, and that's the last entry next to E2. If I now recover what the E0, E1, E2 were from here, that will be the final formula for the polynomial G of P. That will be the final formula for the polynomial G of P. This is a very straightforward example. It just took you so much time to finish this example because it's a free stage construction, and I made an effort and I single out every single stage explicitly so you can see it. After some practice, you will realize you can do some shortcuts and you have this whole picture, and that will be wonderful when you reach that stage. Any questions? All right, thank you very much. It was a technical lecture. Thank you for your patience. Yes, thank you very much. Thank you.